You can tell it. Right, good morning, everybody. So today in the morning, we'll have two lectures dedicated to the specifics of the facility, the Electron-Ion collider. In particular, it's going to be the first polarized electron-proton collider. And very poor, lo and behold, we'll need to measure polarization particles. And the first lecture is by Eyser from Brook National Laboratory. Tell us about polarimetry at the ASC.
Yeah, thank you everyone for coming today. The most generic title I could come up with is polarimetry. I just noticed the shorter this gets, the longer the title of the school gets. Doesn't even fit in one line anymore. So I will talk about polarimetry of high energy particle beams. So in terms of the outline, to give you a little more guidance here, I will start with a little more information about polarized particle beams. How we prepare the polarization, why we need to measure them, which probably relates a little bit to Christoph's talk later in the morning. And then I will focus more on the specifics of the polarimetry, the polarization measurement of the proton beams in the past and in the future at the ENC, and then probably tomorrow about the electron polarimetry. So to get started, I think we should first talk about what we mean by polarization and why we actually need to measure it. Why can't we just assume that it's there and we can use it? So this outline probably has been shown earlier by Thomas and other people. So just a short recap for the electron-ion collider. We want to collide polarized electrons with polarized protons, potentially other light ions, also polarized and heavy ions, starting with silver, gold, maybe lead and uranium. And we want to collide those at various different center of mass energies in the range of maybe 20 to 140 GeV at very high luminosities. And the main part for this morning here is that both the electrons and the proton beams should be highly polarized. So beam polarization should be 70% or more, with very high accuracy, and then we want to collide those beams ideally in this one detector, the EPIC detector that Thomas and Maria, I guess, talked about in great detail, and potentially a second interaction region. And you can see the whole setup. Of course, we come from a proton source here. We go through these various pre-accelerators before we inject this beam here, and then we accelerate this up to 275 GeV. And similarly with the electrons, we have the electron source, we have this rapid cyclic synchrotron, we inject a beam here and we accelerate it to 5 to 18 GeV. And then at the high energy, at the highest collision, we want to make sure that we understand what's going on there. So if you look it up on Google or Merriam-Webster, wherever, what polarization actually means, there's a whole wide range of things that you could refer to for the purposes of our discussion here. The magnetization is the most appropriate because that's directly related to the spin of the particles, right? And when we talk about the polarization here, what we really mean is the average alignment of the magnetic moment of an ensemble of particles. So we know that the protons and the electrons both have spin 1/2, h bar. That's the spin of the particles, but if we talk about hundreds of thousands of millions or billions of particles, the mean polarization is really the number of particles with the spin aligned to an external field minus the particles anti-aligned to that field divided, oh, there's a plus missing here, divided by the sum of the particles. So this polarization can be anywhere from +1 to -1. If the number of particles with plus and minus orientation is the same, then the polarization is 0. It's unpolarized. If there's only particles with spin pointing in one direction and one in the other, it's 100%, and obviously the -1 for the other direction. So why is this important? We go back to what most other people, I think, talked about at the school, the physics that's behind this. We have a physics observable that might or might not depend on the spin alignment. So we measure the cross section with a specific spin alignment plus and the cross section with a specific spin alignment minus. That gives us this polarized differential cross section here. And if we do the measurement with a pure spin alignment, we just measure the events with the plus polarization, with minus polarization divided by the sum of this. That's the asymmetry that we measure. And we all know that this measurement is a statistical measurement. So the more accurate that we want the result to be, the longer we need to measure, the more events we need to measure. But now it turns out that we also have this polarization. So we don't have this pure measurement where we have a well-known spin direction. We have an average beam polarization or scattering polarization here. So we need to introduce this polarization here. And if this polarization is small, you can see that the statistical precision of our measurement directly scales with essentially the inverse of the beam polarization of the polarization value itself. So if the polarization is small, we have to measure a lot longer for the same statistical accuracy of our physics measurement. So that leads us to this figure of merit, which we know is proportional to the number of events that we measure, and it scales with the square of the beam polarization. So the higher our beam polarization is, the faster our measurement will be to get the same result compared to a lower beam polarization. And this goes with p squared. So it's essentially twice as important as the number of events that we have in our measurement. So now talking about the high energy polarized particle beams, I'm essentially starting here with Adam and Eve to give a little bit of introduction how we actually can prepare polarized particle beams, right? So we start with the Bohr model of hydrogen atoms, where we have the energy levels, which we can calculate depending on this quantum number n. We introduce the orbital angular momentum, and then we find that we also need a spin of the electron, which essentially introduces a splitting of the levels by a factor of 2, which tells us that the spin of the electrons is either plus 1/2 or minus 1/2. So it can have two orientations. And this spin now we want to use to separate the particles based on that quantum number. So how do you actually do that? You can look at further the hyperfine structure, which combines includes the electron spin and also the proton spin in this case, the nucleon spin. If you apply an external magnetic field, you find that you can separate the energy levels. So you have these different combinations where you have the spin of the electron, the spin of the nucleon, the proton in this case, and you have these 4 different energy states. You apply an external magnetic field, and you can separate these states here. And now you just have to find a way that if you wanted to spin polarize, say, the electron, you would separate these states 1 and 2 from the states 3 and 4. That seems pretty straightforward. If you want to polarize the nucleon, the proton in this case, you would want to separate the states 1 and 3 from the states 2 and 4. And you can see that separation is not quite as straightforward. So what do you do? We go back to 1922, which was the start of the Stern-Gerlach experiment. And this is the memorial plaque at Frankfurt at the university where this experiment was done. So this actually was a very important experiment to really prove that the spin of the electrons is 1/2, that there are 2 possible states. So what Stern and Gerlach did was they had a beam of silver atoms here, neutral silver atoms, where you have 1 electron in the outermost shell. And they let this silver beam go through this inhomogeneous magnetic field. And if you have an inhomogeneous magnetic field, what you end up with is a force that will lead to a separation of or at least a deflection of the silver beam that depends on the orientation of the magnetic field of the electron in the outermost shell. If the magnetic moment, if the magnetic moment was continuous, randomly oriented with respect to this external field, what you would expect is just the spreading of the beam and the blurred out spot on this photographic plate in the end. What they observed, of course, was something very different, namely two very distinct separated lines that are most separated in the middle, where the magnetic field is the strongest, and then it flattens out like in this I shape on the outer edges, based on how the magnetic force actually separates those two states. But this really tells you that the electron spin is 1/2 h bar. And this already tells you how you can essentially create a polarized particle beam. In this case, it's the silver beam that is separated depending on the spin of the electron in that outermost shell, whether it's aligned with the magnetic field and aligned with the magnetic field. So this setup allows us to make a electron polarized silver beam. If we put a collimator here and only put a block here and only let the upper half through, we would have a polarized beam where the electron polarization is +1/2, +1. So that would give us states 1 and 2. That's not what we want. We want the proton, right? In this case. So somehow we have to either get rid of state 2 and feed back state 4 to get the +1/2 for the proton spin, and then get rid of 2 and 3. So what you can do here is a duplication of the Stern-Gerlach setup, where you have one homogeneous magnetic field that really does what we discussed before. You polarize the electron in your outer shell. You're left with states 1 and 2. And then you use an RF transition unit, a radio frequency transition unit that has the exact right frequency to induce a transition between states 2 and 4 in this case, or you could feed back state 3 into state 2 into state 3, or you could feed state 4 back into state 1. Either of those two would work. It's just a question of how much intensity you're willing to work with in the end, right? So in this case, we do the first setup. We have the transition. State 2 goes down to this undesired state, and then we have a second setup here where, again, we block out state 4 down here, and we're left with a nucleon polarized particle beam here that essentially has 1/4 of the intensity, but that's what we have to live with in this case. Okay, here's a little more information. Essentially what I said before. What I'm not going to talk about in much detail here is that this polarization. So ideally, you would get a 100% polarized, a nucleon polarized particle beam here. There's a limit. Obviously, this depends a little bit on the efficiency of the RF unit, how well it's tuned to the frequency, etc., the magnetic field strength itself. You can see if the separation here is the RF frequency, and also obviously if the temperature is too high, there's some sort of fusion, and you can calculate that. But typically, a source like this, you could probably get polarizations of 85 or 90, 95%. Then you have an electrically neutral particle beam that is nucleon spin polarized. And now you just have to think about, how do you get this neutral particle beam to high energies that you can actually collide them at a few tens or hundreds of GeV to actually make physics with this. So this there's a little more detail about a more advanced polarized proton source. It's actually the highest intensity polarized proton source that has been built in the world, and we use this at RIC. It's called the optically pumped polarized ion source, OPUS. It looks a little different, but essentially the basic components that I just explained are still in here. So you start with a positive hydrogen beam of a few keV just to get you started. Then you neutralize this, you give it an electron, you do these transitions here, and then you find a way to strip off the electron without losing the polarization of the proton that you want to work with. And then out of the source, you get a few tens of keV charged proton beam that you can then feed into your pre-accelerators, the AGS, into RIC, or later on into the Electron-Ion collider. And as I said before, so the current of these bunches that come out here on the order of a few milliamps, and this would give you one bunch that you would either get in RIC or in the EIC with a polarization of 80% out of the source or 85% out of the source. And then you have to accelerate those particles to the energies that you want to work with. Let's see. I don't want to get distracted too much on this one. I don't know how much Christoph is going to talk about this, but we should mention particle beam optics, because what we are going to work with is a circular accelerator or collider. And the immediate question that you should have is, why don't we just use a linear accelerator? All we need is an electrical field to accelerate particles, and we probably don't have to worry about any losses of polarization or anything else. Well, it turns out circular accelerators are much more efficient because particles go in circles, and you can reuse the bunches and particles that don't do anything in the experiment. And they're also much easier and cheaper to build because you have this acceleration unit here that on every turn you can reuse, and you don't have to build hundreds or thousands of them in one line. But then you also need magnetic dipoles and quadrupoles to keep the particle on this circular track. You want to focus the beam with quadrupoles and other magnets. And all of these things you can calculate in this photo lattice or F0D0. It's a defocusing setup where you have this envelope and the betatron oscillations. And without going into detail here, the problem with the betatron oscillations that oscillate around a stable orbit is that you can hit resonances, which means that misalignments in the magnets or distortions in the magnetic fields lead to resonance variations that you have these different tunes, they're called, where you have to avoid integer tunes because that is where you would potentially hit the resonance condition and lose the beam. And why am I talking about this? Because it's also important for the beam polarization or the alignment of the spin of the polarization vector in this setup, because the spin, the polarization, is related to a magnetic moment. Magnetic moment, yes. If you use magnetic fields here in the dipoles and the quadrupoles, every time you do that, you have a precession of the polarization vector around the magnetic field here. So the resonance conditions also can apply to the polarization vector itself. And if you have something that's a misalignment or some imperfection here, it can lead to a resonance that leads to rapid polarization loss. So you could end up with zero polarization, especially if you go through a lot of acceleration. You hit these resonance conditions at different energies, and you're left with 5% polarization, whereas in the injection you started with 80 or 85. So you can calculate all this. We can look at this maybe after one of the breaks, or during one of the breaks. The main point here that I want to make right now is that the resonance strength depends on the local orbit distortion, the magnetic fields, and the crossing speed, meaning how fast you can accelerate the particles here. But the main point really for Rick and the electron-ion collider is that the number of resonances depends on the energy that you want to reach. So some of these resonances are equidistant in energy separated by about 1 GeV. So if you want to get a proton beam up to 275 GeV, you have to deal with up to 400, 500 resonances that you need to cross to get there. And each of these can potentially destroy a beam polarization. So I have this, I call this an example. It's the Cooler Electron synchrotron at COSY, which is now decommissioned. It's a very it was a very state-of-the-art machine in Germany at the Forschung Center in Munich. It's a pretty small machine. The circumference is about 180 meters, but it was one of the very early highly polarized proton synchrotron machines where you had a few external experiments and internal experiments. And it very nicely shows how these depolarizing resonances work. So the maximum energy or beam momentum at COSY was 3.3 GeV. That's not anywhere close to 100 or 275 GeV. But as I just said, those resonances are equidistant, and you can see the resonances illustrated on this plot here. So this is a function of the beam momentum, and this is the working point in the y direction in this case. And you can see there are two different types of these resonances. One's called imperfection resonance, which is really just the equidistant at about 600 MeV over C in this case. And then there is another type, they're called intrinsic resonances, which depend on the working point itself and the momentum itself. The main point here is you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 resonances that you need to cross to get to 3.3 GeV. And we're going to look at Rick on the next page. Some of these resonances you just have to deal with, and you have to cross them as quickly as you can in order to lose as low polarization as you can. Other ones that also depend on this working point here, you can minimize or reduce the crossing speed itself if you change the working point. So you essentially try to have an orthogonal crossing of the working point with this green line here. And this is where this so-called air quadrupole, which is a fast magnet that you can fire, comes into play that quickly changes the working point to cross here in one direction or the other direction. And that way you reduce the polarization losses. So this is a polarization measurement at COSY. That was one of the very nice things at COSY, that you could essentially measure the polarization during the acceleration. So the cycle here was you injected a bunch, you accelerated it to the highest energy, took about 5 or 10 seconds, you dumped the beam, and you do that again. So you could do tens or hundreds of thousands of these within the period of a few days or weeks. And then you really have this excitation function here where you can measure the polarization as a function of the energy very accurately, and you can compare what the effect of these resonances is. And you can see some of these resonances actually are so strong that you're not trying to avoid them, but you try to really enhance them and lead to a complete polarization or spin flip. So that's something that's being done at RIC too, where you start out of the source, the polarization is, in this case, 80%. And then this resonance is so strong, and you try to enhance it, that the polarization flips, it's minus 80%. And again, this one here. So the polarization that you use in the end is actually the opposite sign of the polarization that comes out of the source. It doesn't have to be that way. It obviously depends on how many of these strong resonances you have. But that's one way you could also deal with it. So for Rick, I'm not going to talk much about this, just the source here, the pre-accelerators. Then you have the two polarized proton beams that we call the blue and the yellow. They collide at the different experiments. In this case, it says between 50 and 500 GeV center of mass. We usually have 200 or 500 GeV. But for Rick, the picture now looks like this. Remember, before we had 15 resonances. Now we have, again, these imperfection and intrinsic resonances. So there are a few hundred of those imperfection resonances and a little less of the intrinsic resonances. And you see the strength here. And as I said before, some of these you try to cross quickly. Some of them you try to cross slowly and induce a complete flip of the polarization. So I should really move on a little faster here. One way to deal with the resonances is to use these magnetic field setups. They're called Siberian snakes. And what they do is actually they flip the polarization vector by 180 degrees. And they do that every turn, which means that if there's an imperfection resonance that would give a kick at every turn in one direction, and that is what the resonance really causes. If we switch this thing on in one turn, imperfection resonance, or this imperfection in one of the magnets gives a kick in one direction. Now we flip the polarization in the Siberian snake. The next time the beam comes around to that same location, the kick goes in the other direction. So we could completely essentially remove the effect of some of these resonances and only deal with the intrinsic resonances. So we have a few of these devices in the two Rick beams, and we will use the same devices at the Electron-Ion collider. This is more detailed about how this spin motion works through the Siberian snake. If you're interested, we can talk about this later, or you can look at it. It's really, it looks super complicated. It is super complicated, but it's actually very neat. Where you have the different spin components where you come in. This is a vertical polarization. When you come into the this SY is a vertical polarization. You come into the this spin rotator, the snake, and you can see it goes on this roller coaster ride where you have the XY position here on the right side, and this is the magnetic field strength and the different components. And this thing is symmetric, so these outer ones are essentially the same, and the two inner ones are the same. So it's a symmetric setup, and you come in with this SY +1, and then it goes in this direction, and you come out with SY -1, and all the other components, they do crazy stuff in the middle here, but they come out to be 0 in the end too. And you can tune those in different ways. You can make it that this would be SX and the other, so a sideways polarization, or you could come in, if you change the magnetic field here, you could turn a vertical polarization into a transverse polarization, a sideways polarization, and different things. Yeah, this is how this looks for Rick. As I said, COSY was very nice because you could essentially measure through the acceleration cycle in every 5 or 10 second interval. At Rick, it's a much more statistically challenging process, and you can't do that during the ramp or the acceleration. So you have to use different setups where you have this this flat. So this would be the injection energy. And then you would need one setup where your flat top sits somewhere at 120 GeV, at 160 GeV, and 250 GeV. So this is a very much more involved measurement. You can see the statistic uncertainty obviously is not nearly as good as on the previous plot. I'm going to skip this one here. Synchrotron radiation, I think we can touch on a little more tomorrow because it's more relevant for the electron beams. So quick recap for our requirements for polarimetry. We know electron beams between 5 and 18 GeV, the proton beams between 41 and 275 GeV. Each store, and I have mentioned that, so we store the beams for the collisions at the highest energies, and then we run the experiments for something on the order of maybe 8 hours or 10 hours. So the stores are pretty long, and there might be polarization decay at the highest energies. Also, the beams are bunched. So at RIC, we have 120 bunches. At the EIC, we will have something like 1,200 bunches in each machine. And the bunches will have essentially their own bunch polarization. So some bunches have polarization up, some bunches have polarization down. So we need to be able to distinguish the different bunches and measure the polarization for each bunch separately. The bunch spacing is really short. Right now, it's a little over 100 nanoseconds. At the EIC, it will be 10 nanoseconds. So the bunches are very close, but also it means that our polarization measurement needs to be able to resolve the 10 nanoseconds or much better than that. So in order to give a full measurement of what we want to do and what we need to confirm is, first of all, the requirements for the physics program, the relative uncertainty on the polarization measurement should be 1% or better, both for proton and electron beams. We need the time dependence, meaning the polarization decay throughout the 8 hours. The decay might be small. Say we start with 70% and after 8 hours, the beam polarization is 65%. It's not a big difference, but we need to know how large that is. As I said, we need to be able to separate the different bunches in our polarization measurement, especially if consecutive bunches have different orientations. So if one bleeds into the other, that's more dangerous, or that's worse than having one that's unpolarized with one that's polarized. So it's a different sort of dilution. What I haven't mentioned yet is that the bunches have a transverse size. They also have a longitudinal size, obviously, but they have a transverse size. And from RIC, we know that the bunch polarization has a transverse profile. So the polarization in the center of the bunch is higher than on the outside or further out of the bunches. So we still need to be able to measure that. It would be nice to measure the polarization during the ramp, just to make sure that we understand the machine and how the resonances work and how we can deal with them. So if we just measure at, say, 100 GeV flat top energy and the polarization is 50%, and we know the source polarization is 80%, we would like to understand where we lose the 30%. It might be somewhere here, or it might be from 24 GeV up to 100 GeV. One of the resonances might be too strong. So that's something that really helps understand the machine and improve the value P in absolute terms. And then also important, and I haven't mentioned this yet, the polarization vector at the experiment. The stable polarization direction in the machine is transverse. So if the beams go in this direction, this would be the stable polarization direction, either up or down. But in the experiment, for the electron beams and also partially for the proton beams, we want longitudinal polarization. So there will be a spin rotator that I skipped on the previous slide. It's a similar setup to the snakes that I talked about in more detail. It just rotates a vertical polarization into longitudinal polarization. But we need to confirm at the experiment that the polarization really is longitudinal. And that's probably one of the biggest challenges for the proton beam at this point.
Sorry, I have a random question. Can you go back? And I mean, really, really random. I've never noticed it before. Did you see that? It's like, I thought that naively thought that the red ring would be more like a ring, but then it has these like,
This one, oh, this one?
that one, it has those like little bumps, you see? Like,
Well, this one is super exaggerated.
okay.
So at the EIC, the I don't know if
I
Chris
might just
now
be
left.
drawing a schematic.
So
wasn't sure that was-
I would assume that Chris was going to talk about this in more detail.
Okay,
So at the EIC, the electron and the proton, so I should say the red is the electron beam, the yellow is the proton beam. And they cross each other in each of these 6 interaction points, except this one here. So it really, the electron beam is outside of the proton beam here and then inside of the proton beam here. Whereas in Rick, that's not really the
Okay,
case.
okay.
So it's super exaggerated,
okay.
but it really is what's happening. And then there are more details here about this bypass. I'm not gonna,
Right, thank you.
maybe Chris will talk about this. Okay. Now to the main part of today. The hadron beam polarization. This is actually my favorite slide because this shows you what's happening. And now, so this on this slide is the proton bunch, as you can see. These are protons. You can see the polarization or the spin direction of each of the protons. So I have 16 protons here. And now you want to figure out what the bunch polarization is. So it's not quite as easy if you try to follow it along. It already gives you a hint of what you try to do, right? You try to interact with the protons here and get the measurement out. I don't know, is the polarization high? Is it not? Can't really say. But the nice thing is we're in a circular accelerator or storage ring. The bunch comes by every 13 microseconds. So every 13 microseconds, we can use it to try to learn something about the bunch polarization here. Now here on the right side, it's sorted out. As I said, there are 16 protons in there. I sorted them by spin here. So you've got 12 with spin up, 4 with spin down. Naively, that looks pretty nicely polarized, right? But if you calculate the polarization that I had on slide 2, I guess, the polarization really is only 50%. So this is not good enough to for what we want to do in the end. But that's just a side note. So getting a high polarization is actually more challenging than you actually think, because you have this difference in the denominator here, in the numerator. Okay, so what we need to do is somehow find a way to measure the spin alignment of the protons in the bunches. And measure already tells you what we need to do is somehow an experiment or some sort of interaction that tells us what the alignment of the different protons is. The bunches, I have 16 protons here. At REC and at EIC, we will have 100 million protons in each bunch. So it's really 10 to 11 times the number of bunches. So that's a lot. So we can essentially use some of those for our polarization measurement without affecting the bunch very much for what its primary purpose is on the experiment. So we will somehow find a way to scatter some of these particles. And on the previous slide, you tried to do that by using photons, right? You looked at it, you tried to figure out what was going on. In this case, if we were to use photons, it would affect these protons itself. So it would be a scattering experiment. And we can try to find other ways or other means to do this, not necessarily a photon. The photon is probably more important tomorrow. So then we have our scattering probability, and we need to find something that depends on the spin or on the alignment of the spin. So we have the unpolarized cross section here, and then we have a spin dependent part that should be different depending on whether it's plus or minus polarization. And then we just calculate this asymmetry that we always use, which is twice of the spin dependent part. If we divide it by the sum of this, then we just have the epsilon itself. So whatever experiment we use to measure the polarization, or in the experiment, actually, we need to find a frame that we can use to describe this. And as I said before, the stable polarization direction in the ring is vertical. So we have our beam particle here, and we have something in this case that's a fixed target where we collide the beam on. The stable polarization direction is vertical. That's normal to our scattering plane here, and normal to the beam momentum. So we have the normal direction, we have the sideways direction, and we have the longitudinal direction. And then we look for a reaction in this scattering plane where we could measure a symmetry where we would have something different on the left side than on the right side. And then we introduce this analyzing power, also what's used in many experiments further down for the main physics purposes, where we have this asymmetry, which is the difference between our left events minus the right events divided by the sum of the two. We have the physics observable here, our analyzing power, and then the beam polarization here. So this is what we want to measure in the end. This is what the polarimetry is supposed to do. Here's a physics observable that right now could be anything, but it should be non-zero. That's the most important part. There should be something that's going on here. So it's effectively a chicken and egg problem, right? If we knew the polarization, we could calculate the analyzing power. But we want to have the analyzing power to measure the polarization. So where do we start? We find a reaction where we can measure the polarization, and then we use that to measure the beam polarization. And conveniently enough, we can look at elastic scattering. So we have the beam protons here, and we use target protons here. So we have the scattering PP, and then we measure elastic scattered proton that might come out to the left and elastic scattered proton that might come out to the right. Now, since these two are indistinguishable, it also means that if we have this elastic scattering, one always goes to the left, one always goes to the right. We don't know which one. So it might be that this is a small angle scattering, this goes slightly to the right, and the recoil goes almost under 90 degrees to the side. Or it could be the other way around, and this one goes slightly forward, and this one goes almost 90 degrees to the right. The important thing is that we can use the symmetry, even though they're indistinguishable, and we can say that if our beam particle is polarized, we measure an analyzing power, an asymmetry, I should say. We measure an asymmetry. And if the beam is unpolarized, but we polarize the target, we can measure a similar asymmetry. And those two asymmetries have to be the same if the polarization values are the same. So the analyzing power of the two are the same. You can write this down very formally in the scattering matrix, where you have the initial state polarization. It could be normal, sideways, longitudinal, or zero, unpolarized, the same for the target. So you have the scattering matrix here with the four different states. And the main point, and you have those indices here where you have, I should go through this also. You have four different indices. One is the projectile, one is the target, one is the scattered particle, and one is the recoil. So all of those could be unpolarized. One could be polarized in the normal direction. One could be polarized in the sideways direction. You have all different combinations of 4x4 matrix, but the main point here is that A00N0 should be the same as the A000N. So whether this one's polarized or this one's polarized, the analyzing power is the same. And what does that mean? It means that we can calculate the asymmetry of both polarized measurements, the asymmetry with respect to the beam, the asymmetry with respect to the target, and they should behave the same as the ratio of the two beam polarization and the target polarization. And now the target, as I said, this is a fixed target. we can find a setup where we can measure the target polarization independently of this experiment, meaning outside of the interaction region itself. So we will have the measured target polarization. We measure these asymmetries, and then, and I should actually remove -2. Find me, please. And then we can calculate the beam polarization. So this is what was done at COSY, and this is what we have done at RIC. So we have two detectors here where we measure the left and the right hemisphere. As I said before, this is the scattering plane where the polarization direction is normal to the scattering plane. In our experiment, in the statistical sampling, those two are not always the same, but they can be rotated into each other. So we introduce this azimuthal angle phi here, which means that if our polarization is vertical here, the analyzing power with the asymmetry is largest in this direction. If we measure it in this direction, the asymmetry will be very small. That's just illustrated down here. But we can use this to just place our detectors to the left and the right side because it's illustrated here. And then we measure those asymmetries. Okay, this is back to my easy. Yes.
Because it's about that part. But this is, you do like, as you're setting up, like as you're warming up the beam, because like, do you move the target? Do you put the target in?
No,
Always there.
I will talk about this a little later. There are different methods. Really what you, so I said the beam is bunched.
Yeah.
Let me just, at RIC, we have 120 bunches. On average, we try to have 60 bunches with a plus polarization, 60 bunches with the other polarization. So we can just use that and make the experiment. And then we have the target where we can flip the target polarization. And we do that every few minutes. Now, if you average this over, say, 8 hours, the average target polarization is pretty close to 0. And the average beam polarization is pretty close to 0. We just sort it in different time bins, say. So we know we just sort it with respect to the beam polarization and ignore the target polarization. And we do it the opposite way. Okay, so this is how this was done at COSY, how you would measure this elastic scattering. This is a very ingenious setup, I think, which was one of the early experiments here called ETA, where you really used only scintillators to identify the elastic scattering, the elastic PP scattering, and that's purely based on the kinematic correlation of the elastic scattering itself, meaning that the azimuthal angle is back to back, so phi1 minus phi2 is pi. And then you have this kinematic correlation here of the polar angle, which depends on the center of mass energy or the collision energy in this case. And then you really only have these scintillator bars that those allow you to measure the phi. And you have these scintillator rings, which allow you to measure the polar angle. And the size of these rings actually changes such that the resolution of the polar angle is the same across the whole range. And then you have these scintillating fibers here, which allow you to calculate or measure a point here, and then you have all the values that you need. And then this is what the setup looks like for the target. So we have the proton bunch, which comes through here. And this is the target setup. So this is essentially what I talked about earlier for this Stern-Gerlach, the Bright-Rabi setup, where you have the hydrogen beam here. You have one of these 6-pole magnets that sort out one of the two of these states. You have an RF unit here, which flips one of the states away, and then you have the second magnet here, which removes another one of these states, and you're left with essentially state one. And then you have a magnetic field set up here, just Helmholtz coils, where you can every few minutes, say every 5 minutes, you change the current in the setup here, and you switch the magnetic holding field, which defines the polarization direction of the target. You change the current every few minutes from up to down and up to down. That way you can measure the target asymmetry. And then on the back side here, and this is what I alluded to in the previous slide, you have an analyzer, a Bright-Rabi unit, where you again have an RF unit and another 6-pole magnet, which allows you to change some of these states again, and you have a mass analyzer here, which allows you to, depending on the settings of this one, allows you to measure the intensity of the beam that comes through. And depending on the ratio of the different states that you want to measure here, you could calculate what the target polarization is in this region. So this is the last part that you need, in addition to your two different asymmetries, to really calculate the beam asymmetry, the beam polarization. Okay, now we go to RIC. This on the previous slide was again 3.3 GeV momentum. At RIC, we're at 100 or 250 GeV beam energy. There is an asymmetry, this analyzing power. It's much smaller than at the lower energies, but you see it's still on the order of 4 or 5%. In this case, as a function of minus t of the momentum transfer here. But I think what still impresses me the most is that with a proton beam of 250 GeV on a proton target, you can measure elastic scattering. So there's a elastic scattering of two protons, and they don't break up or anything else. They just nicely scatter off each other. And what you measure here is, because the elastic scattering, obviously the scattered particle with the high energy is very forward. It doesn't even leave the beam pipe, but the recoil proton from the target comes out under almost 90 degrees, and it has very low energy. So you have a 250 GeV proton beam that hits the target, and in your detector to the side, you measure a proton that has something on the order of 2 or 3 or 4 MeV. So it's very low energy. It's not nearly relativistic. You can describe this in this formalism of this. It's called the Coulomb nuclear interference region, where you have different scattering amplitudes, which have a no spin flip or single spin flip and double spin flip. I don't find that particularly interesting. You can calculate, so the curves here, I mean, obviously it's interesting in itself, but you can describe the measurement and use that for your input analyzing power if you wanted to. But really, the most impressive for me, as I said, is there's elastic scattering at these high energies. So this is a calculation where you have the kinetic energy of the recoil protons. As I said, it's very low MeV energy range. And then you have the recoil angle here, which is 90 degrees minus theta. So this is almost sideways at maybe half MeV. And then you have this kinematic correlation here that you can just calculate. And at 10 MeV, you have a scattering angle that's 5.5 degrees off of 90 degrees to the side. So this is the region where we would place a detector, and it's kind of illustrated on here what we do. We use silicon strips that have a certain width, so we can measure the scattering angle by the number of the channel that we use, and then we try to measure the energy of the particle in that detector. In addition to that, we also try to measure the time of flight to make sure that it's proton. So, I don't think I should go into too much detail here. This is how this looks at RIC. This is the so-called polarized atomic hydrogen jet target. So it's polarized, it's atomic, and it's hydrogen, and it's a gas jet. So we have the same setup that I talked about before. We have essentially a hydrogen gas bottle here. Dissociate the H2 into a single H's, and then we have these two magnets here that sort out some of these hyperfine states, and we have an RF transition unit here that induces the transition between two of them. And then here is our interaction region. So the beam goes in this direction, hits the target that comes through here. And this gas target is actually, it's a very thin gas target. The transfer size is about maybe on the order of a centimeter, full width at maximum. The beam that goes through there has a transfer sponge size of less than a millimeter. So, oops, sorry. No, wrong direction. So this is our interaction region. And then these two chambers here show you where the detector sits. And that again is really under 90 degrees to the side. And then we go down here to have our analyzer in the bottom, ideally. So this puts it together with what I talked about before. We have this scattering plane here. Here's an illustration of how the kinematics look like. We have the target here, which is a little diffuse. As I said, it's about a centimeter across here. The proton beam comes through. We have the scattered proton that is almost the direction of the beam. So we have no chance of measuring this the way that we did it at COSY, where we had both particles. Here we only have one. So we have the recall particle here, and this is highly exaggerated. So this detector here, you can see it here, sits about 70 centimeters to the side, and the detector itself is pretty small. It's about 10 centimeters in total length. So it's really very far to the side. And we have the strips here where we know the location, we know the angle. We can measure the energy, and we can measure the time of flight to do the two different things that we need to do. Namely, so we have, this is from a very simple toy Monte Carlo simulation. It's really just a random generator and root where you apply a little bit of smearing. And what you do here is you calculate the time of flight for a proton as a function of the kinetic energy. As I said, this is a few MeV, so it's highly non-relativistic. So you just use classical mechanics here, 1/2 mv squared. And the time of flight for those 70 centimeters now is on the order of a few tens of nanoseconds. So it's pretty slow. As a reminder, the bunch spacing at RIC is 100 nanoseconds. So this is still well within the next sponge within when the next sponge comes through. Now we have the silicon detector, which has a finite thickness. It's a few hundred nanometers. And at some point, you have the EDX in the detector, which you want to measure. So this is the measured energy in the detector. At some point, the energy is too high, and the protons start to punch through the detector itself and leave the detector. So at one point, the measured energy is not anymore the energy that the protons have, and the measured energy actually starts to decrease because the DEDX is smaller at higher energies. So it reaches the minimum, but we're not anywhere close to that. And then at this point here, our detector acceptance is essentially over. So at this point, the angle itself is too large and we don't have it covered anymore. So this is from a simulation which only includes some very naive smearing in terms of the energy resolution and mostly in terms of the timing resolution. If we look at the real data, it looks like this. The scale is almost the same. So it's between 1 and 7.5 MeV. The time of flight, it cuts out at around 70 here, but you can see the timing resolution and the energy resolution is much worse. There's a whole lot of background you can see here, although this is logarithmic scale. So this region is not that bad, but you can see the punch through here. And what's actually not even shown here is this region down here, which is mostly populated by highly inelastic stuff. So this is all elastic, right? This includes, as I said, the beam has, in this case, the beam is 100 GeV. So the elastic part is a fraction of the total stuff that happens in the target. So there actually is a lot of hard scattering of the protons, which could produce photons, charged pions, and they sit essentially in this region here where you have, they're moving with the speed of light. So they sit in this region here. They can be from more upstream or more downstream than the target itself. So this is high background region here where if I included this region in the plot, it would probably define the red, and the elastic band would not be visible anymore. Right, not tonight. Okay, so now this introduces the different silicon strips, as I said, for the different angles. Those silicon strips are pretty narrow. They're 1.3 millimeters wide. And we have, in this case, we use 12 different silicon strips here, but you can see the kinematic correlation here. So this one gives us a particle ID, because this depends on the mass of the particle, right? The time of flight with respect to the kinetic energy. The kinematic correlation of the recoil energy with the angle allows us to select elastic events. And those are the two things that we need to do to reduce the background in this plot here. So this is the same plot on the left side here is now split up for the different strips that we use. And they're not all the strips. You can see there are gaps between. So this would be the first strip. I think this is the 4th, the 8th, and then the 12th strip. So you can see how the kinematic correlation for the different angles here actually gives you a different region of this band that you're sensitive to for the protons. Okay, so we essentially now have everything that we set out to do to measure the absolute beam polarization. Now at Rick, it's a little more complicated because we have two beams at the same time and they use the same target. But let me just go back. We have dedicated detectors for each of the beams, right? Because since this is elastic scattering, this scattering angle can never be smaller than or larger than 90 degrees if you go around this way. So we have one detector that sits downstream of the yellow beam. Oops.
So I don't think I'm fully understanding this thing. So I understand how you're measuring. I believe I'm capturing the information you're saying of how you're getting the polarization. But then is the scattered proton what ends up colliding, or that's where I'm getting a little confused, because you have this interaction with the fixed target there. That might always be there. I'm not sure. I think it is.
Yes.
That you have all that set up.
The jet target is always there.
So then when I think of blue beam and yellow beam, and what actually goes into the collision, would it be that scattered proton after you measure the polarization, or am I
No,
thinking about it wrong?
no. So I actually should have included, I forgot that. I should have
It's okay.
put a Rick overview here. I actually have it. But anyways, so this is the blue beam.
Yeah.
Here's the target. So we have what we call the projectile.
Yes.
And we have the target, and then we have the scattered proton, and we have the recoil.
Yes.
Here's our elastic scattering.
Yeah.
And what we measure is the recoil proton
Absolutely.
and
But then I'm star. What does star measure?
this, okay, and this is where I messed up.
Okay.
So the
Sorry.
we can use this one. So star sits here,
Yeah, yeah.
and here is where we have our beam collisions.
Uh-huh.
Polarimeters at RIC sit at IP12.
Okay,
So they're at a very different location. And the beams are not colliding here. They're slightly vertically displaced. So they're not, the beams don't see each other, but they both see the jet target.
yeah. So the thing that keeps, not the thing that gets measured on the silicon detector, but what keeps going forward is what collides at the interaction point.
Yes.
Okay.
So as I said, each bunch has 100 billion protons. So a few million we take we use at the polarimeter.
Okay.
The rest just goes around back to star or S Phoenix or wherever. And
But what do you mean? Sorry.
we essentially sample something of the bunch, but it doesn't really have an effect on the bunch intensity.
Okay, that's fair. Okay, I see. Sure, thanks.
Okay. Okay, so I also should have displaced these here a little bit. Because this is. So we have the yellow beam that hits the jet target, and we have the blue beam that hits the jet target. The elastic recoil protons from this interaction will end up a little forward in this part of the detector, and the elastic recoil from this interaction end up in this detector. So now you can look at the numbers of events that helps you as a function of the bunch number here. What we measure in the yellow detector that looks like this. So there's a few 10,000 events in here. And then we have something at RIC and also at EIC where we'll use this. It's called the abort gap, which essentially is an unfilled part of the possible bunches that you could use. And you can see if you only look at the yellow region of the detector here, there's a region where there are a lot less events. And if you look at the blue side of the detector, you see there's a different region where there's a lot less events. So this allows you to say something about how the two beams are essentially synchronized to collide at star or S Phoenix if you want. And you're going to use these events here. They're also labeled differently. So inclusive means that you have both beams on the target, so there's potential background contribution from the other beam, but there's also a region here where you only have bunches in the yellow beam. So this is a pure signal measurement essentially, and the same for the blue here. You can see that they're not aligned, so you can really look at them independently. And this will eventually help you to reduce the uncertainty on the beam polarization measurement. So this is a repeat of what I said before. Right? We have the target polarization, we have the two asymmetries. We measure the beam polarization here, but if you write this out a little more detailed, you can see that, as we've seen on the previous slide, there's background there. The background might be polarization independent if it's really hard QCD, hard scattering. The background very likely is either not polarization dependent or very weakly polarization dependent. So to treat this background as unpolarized, polarization independent. So in the denominator, in the numerator, it cancels and it only shows up in the denominator. So it effectively leads to small dilution, but it will do the same for the beam and the target asymmetries. If there's a polarization dependent background, it will not, it will also, it will introduce different contributions here depending on the beam and the target. And they might have different polarizations, obviously, right? So if the background is polarization dependent, you will need to find a way to measure that and estimate the background fraction. And I don't know if I should stop here. Yeah, I think
As you see fit.
I will probably stop here. Because you should also have a break, or if there are other questions, we could finish this up tomorrow. And then move on to the electron beams. And I'll be happy to answer any other questions or.
Excellent. That's thank you.
So I have two questions. First, you said that in one bunch, there's about 10 to the 11 protons, right? So of those 10 to the 11, roughly how many events do we get in like one turn?
And so,
Yeah,
so
we can
far
actually-
I've only talked about the hydrogen jet polarimeter. The answer to that is about 1.
Okay.
I think, so the rate in the silicon detectors for the rate in these detectors, pretty small. It's a few hundred hertz.
Are all the protons that didn't collide, do roughly all of them get reused again?
Yeah.
Oh, okay.
So I mean, you can look at the bunch intensity, so the numbers of protons, Chris might talk about it or not. So there are devices in the machine, wall current monitors, which pick up an induction, and you can measure essentially the current in the machine. And they're very precise. And over the course of 8 hours, the burn off changes by, I don't know, a few percent. But per revolution or per turn, it's completely negligible.
And then you might talk about this tomorrow, but can you talk a bit about how the Sokolov turnoff affects?
Yeah, that's tomorrow. That's for the electron beam. There was a slide earlier that alluded to it, but that's completely irrelevant for the protons, and we'll talk about it for the electrons.
Thank you.
I wrote down that the polarization states come in bunches of every 10 nanoseconds. Does that mean? Because I remember you talking about flipping the states.
The beam is bunched, so it's not a continuous beam. At RIC, we fill bunches that are about, I don't know, 3 nanoseconds long, so about a meter long. And they come every 106 nanoseconds, so they're spaced by about 30 meters. And at the EIC, the bunches will be much shorter, about 6 centimeters, and they will come every 3 meters.
And each of those bunches are spin flipped?
They're not, strictly speaking, spin flip. Each bunch has a well-defined polarization direction, and we can choose what that would be, whether it's up or down. And usually what we tried, or what we did at RIC, is we tried to distribute the bunches as evenly as possible. So we would have alternating bunch polarizations up, down, up, down, up, down, because that allows us to reduce systematics on a time scale of 106 nanoseconds. So anything that changes on time scales that are seconds, hours, days is pretty much irrelevant for this then. So that's what you try to do, and then you also try to reduce effects that might depend on this fill pattern, right? So if it's up, down, up, down, up, down, and you do that every time, you might run into other problems related to how you fill the machine. So we also try to alternate on different fills, like on different days, we use up, down, and then the next one we use up, down, up, down, or we use down, up, down, up. Right?
$150 beam colliding with this fixed target. And 250 GeV beam, they see elastic scattering. So you run your car to a brick wall, the car is 60 miles per hour, and it's like, no, I just deflect a little bit. Explain. 6% of theorists here. Why is it happening? Very high energy beams colliding with targets that they use, they see elastic scattering.
I thought they weren't scattering directly. I thought you said they were like brought near the target.
No, the beam
Oh.
hits directly on the
Okay, yeah.
target.
But tonight, we'll have it.
I mean,
Oh, we don't-
I could understand that there's elastic scattering, right? A certain fraction, but if you compare all the background that you see, it's actually a really large fraction.
For tomorrow discussions. Okay. Let's go. Let's thank Oleg. Half an hour break. 11. Second. Good. Thank you. No, no.
Well, you made me full.
Yeah. And I.